All right, so we're going to start chapter 11. This is going to be our starting point this semester, and we're going to be taking a look at vectors. Vectors tend to be a pretty straightforward idea in terms of conceptually, whereas some of the other things are a little bit more abstract. So I think it is a good place for us to start, and it will help those of you who are taking physics as well that you have encountered them here before you encounter them there. So we're going to start with a little bit of notation and descriptions. So in order to describe the velocity of a moving object, we need to specify both its speed and direction. Okay. So velocity is kind of like speed, but the direction in which it goes is involved as well. We can represent such a quantity graphically as a directed line segment, and you can think of that as a ray. We denote the directed line segment extending from the initial point P to the terminal point Q by what looks like a ray, PQ. Okay, that's geometry kind of notation that you've probably seen before. We refer to the length of it as its magnitude. So magnitude means length. And the notation for finding magnitude, it looks kind of like double absolute values, right? Mathematically, we consider all directed line segments with the same magnitude and in the same direction as equivalent, regardless of their initial point. And we use the term vector to describe any quantity that has both magnitude and direction. Okay, so we could write like, a list of terminology that says vector and write a definition and then something, right? These are all intermingled together. So I feel like a paragraph kind of merging them all together makes sense in this context. So you're going to think of things like rays. So they're going to look, I didn't mean to do that, like this. But if this one right here, what I'm doing on my screen now is I'm copying it. So when I paste it, it's going to be exactly the same direction and exactly the same length. These are copied images, right? We would say that those rays are the same. Those directed line segments, those vectors, they're the same. Because it doesn't matter where you start and end. It only matters that the directions match and the magnitude or length matches, and they do. So these would be the same vector. Okay, that's a little different than we think about in most geometric senses, right? That's a little bit different. So when we're taking a look at these, oh goodness, just a second. All right, clean slide, there we go. All right, so we're gonna find a vector that has an initial point A and a terminal point B. And if you can imagine doing this sort of as a picture, and I'll show it to you as a picture first, just to give us sort of the imagery of what's happening, and then we'll talk about the fact that we don't really have to draw it each time. But I want you to see what's actually being asked of you here. So if we draw just a regular coordinate plane and we plot these points, so I have 1, 1, and then I have -2, 4. And what I'm supposed to do is I'm supposed to start at A and end at B. That's what the directions said, right? It says initial point A. I should have labeled them. Let's do that. Here's A. Oh, goodness. Try again. Here's A. Here's B. So we're going to start at A, and we're going to end at B. And so this is the vector we're talking about. Yep. Okay. The way that we actually find the vector, though, has to do with recentering that vector I just did. And it's like I'm picking it up and I'm moving it back to the center, or the initial point being the origin. So in a very real sense, what I'm doing is I'm taking this vector and I'm shifting it down here. That's what I'm doing when I'm finding a vector. Okay, I'm just saying, okay, well, it's the same vector if it started at 0, 0. So we're going to do this shift to it. Okay, so it's here, but it's going to be the same as the one I just created, which I'll copy it and now and do it. And it would actually be here when I find my answer. Okay, so how do we do that? Well, first of all, you should know that when we write this out, we're going to use that notation that looks like rays. Okay, it's going to look like a ray. And we're going to take the ending point. We're going to use these triangle kind of brackets. Okay, that's how we write vectors. They're going to look like these kind of braces. And we're going to take the ending point's x value, which is -2, and we're going to subtract the initial point's x value. Right? This is how you find distance between things, right? You subtract values. All three of my kids are in geometry this year, so this is going to be fun. I'm teaching trig, they're doing geometry, and we're in Calc 3. Lots of geometry all at the same time. And they did something with distance the other day. They're subtracting values, right? We're doing the same thing. So we're just going to subtract the x value of point A. And then I'm going to put a comma, because that's my x coordinates, and I'm going to do the y coordinates. So I'm going to do the y coordinates of the terminal point. So what's the y coordinates of my terminal point? The y coordinate of my terminal point.
Shouldn't be 4 minus 1.
Yep, it'll be a 4, and then I'll do minus 1, because that is the y coordinate of my initial point. And we're going to write down what we get. So negative 2 minus 1 is, negative 3, yeah. And then 4 minus 1 is 3, okay? And can you visually see that sort of makes sense? I mean, I know my graph is a sketch. I didn't do it on a grid or anything like that. But does it sort of look like it's ending at the point, negative 3 for x and positive 3 for y?
So this is fine.
Seems reasonable.
To the origin?
It's finding what the end point would be if we had an initial point at the origin.
Okay.
And that's how we write vectors, okay? So this is the vector it's looking for. There is one other way to write vectors that you need to be aware of, because your book is going to use them interchangeably for this entire chapter and for chapter 12. And what that is it uses those as sort of coefficients, and it uses letters I and J. And it puts these little hats on them. This is the I component, and this is the J component. And in a very real sense, I is representing the same thing that X would be, and J is representing the same thing that Y would be. And it won't be too long, and we'll get into 3 dimensions. Yeah.
In WebAssign, it's always super specific with our notations. Which one should we use for that?
It should tell you which one it uses. Okay. It should tell you, or it'll use both. Yeah. Okay. So I know there was a lot of me verbalizing what we're doing along with this problem, but this problem is really a fast problem to do. It's just a subtraction problem, right? So when you're looking at this list of problems like Adrian did just a little while ago and been like, man alive, they're at the very end, by the way. The written work problems are at the very end of this paper that I gave you. It looks like there's a lot of problems. They're not all quite as fast as this one, but generally speaking, they all compute really quick. It's arithmetic we're doing here. Okay? All right, let's try another one. So do you see now we've got hats on these things. The hats represent vectors, just like the directed line segments represent vectors. We typically, sometimes you see them used interchangeably, period, but we typically see the hats when they're represented by a single letter, like it's vector A, and then put a hat on top of it. And then when they represent the vector like we did over here with the A and the B, like the initial and the terminal points, we see the ray looking symbol on top. That's typically how they're used, okay? They sometimes interchange them, like I said, but typically. Okay, so as you're taking a look at these, they're asking this is a lot of parts of this, but again, it's all arithmetic, okay? So it says we're gonna compute A hat plus B hat. And we have 2 vectors given below. Vector A is 2, 4, and vector B is 3, negative 1. So what do you suppose we're going to do if we have to do A hat plus B hat? Don't overthink it. What's it going to do?
Add them together.
You're just going to add the X components together, and you're going to add the Y components together. That's it. Okay, so we're going to do that. This is part, I'll label them as A through whatever. This is part A, B, C, D, E, and F. Okay, so here's A. So if we're going to do A hat plus B hat, I'll write it out detailed instead of just getting to the answer, just to make sure everybody's clear on what we're doing. If you look back later, we're going to do the 2 plus the 3 and the 4 plus the negative 1. And what is that going to give me? 5, 3. Thank you. 5, 3. Everybody good with that? All right. The next one says that we're going to do 3 and then A hat. So what do you suppose that's supposed to tell you to do?
Multiply 3 by the 2 points.
Yeah, so notice the 3 in front. It's a coefficient, right? We sometimes call them a scalar. It's a scalar multiple. It multiplies through, and we're just going to multiply the 3 through the vector A. So we're going to take 3 times 2 and 3 times 4. You do not need to write that out for me, by the way. I'm just going to write it out on my screen for now. And once we do that, we're going to get 612. Okay, everybody good with that? Hearing no complaints, I'll continue. C. So C says that we're supposed to do A hat minus 2B hat. Okay, so what's this telling you you're going to do? So go faster if somebody just tells me.
The x of a minus 2 times the x of b as well as the y of a minus 2 times the y of b.
Okay, so I did the x ones first. Does everybody see? So we got the x value of the vector a minus 2 times the x value of the vector b, and then we do the same thing with the y values. So the y value of a, which is 4, minus 2 times the y value of b, which is negative 1. And again, I don't need you to necessarily write those out. You can do arithmetic in your head. These are small numbers, all that. That's fine. What are we going to get? I think I have negative 4, 6? Negative 4, 6. All right, D is without a doubt the most interesting one we've seen so far. It does have the addition, subtraction kind of scalar multiple notation as the last one, but what else does it also have?
It has the magnitude.
It has the magnitudes listed, right? So I'm going to do this kind of in 2 steps. The first step I would like to do is to actually find the part that's between the magnitude notations, and then we'll talk about what it looks like just in general to find magnitudes, okay? So we first have 5b hat minus 2 times a hat. And notice the notation went a different direction, so be careful. This one's got b at the beginning, a at the end. So we need 5 times the x component of b, which would be 3, minus 2 times the x component of a, which is 2. And then we have that 5 times the y component of b. So 5 times negative 1 minus 2 times 4. Did I get it written in there right? I think I did. All right, what is my first component after I do the addition and subtraction? I think it's 11. Is it 11?
Is it 3 or is it 2?
Did I miss it? I might have written something down wrong. 5 times 3. Okay, so we're good? Okay, so in fact, let me put it over here. This is 11. And then what's the y component? What is it? Negative 13? Negative 13. Okay, so I want you to think visually what this means. If I draw this on a graph, what does this look like? Well, it starts, come on, and this is just going to be a sketch. Come on. Oh, there we go. It starts at 0. I'm off screen. That's better. It starts at 0, 0. And then the 11 tells you that I go to the right 11 because that's the x component or the I component, right? And the negative 13 tells you that I'm down here in quadrant 4. So I'm down here and it looks something like this. Okay? How can I find the length of that segment? Because that's what magnitude is. Say it louder.
A squared plus b squared equals c squared.
Okay, so what are you using, Adrian?
I'm using the Pythagorean theorem.
Pythagorean theorem. Does everybody see the not visible triangle? Yeah. So I'll draw it in for the sake of this one, and then we'll recognize that there's sort of a formula we can go with. But here's my triangle, or you could draw it back to the y-axis. That would be fine as well. So this one is my component 11. This is technically the component negative 13. When we square it, it will be positive. It won't matter anymore. And so the general form for finding when we do the magnitude of something, right? So this is 5b minus 2a's magnitude, is that we take the square root of each component squared. So the first one was 11. The second one, I know it's a negative, but we're going to square it, so I'm just going to write the positive part in because it doesn't matter, right? So I square one component, I square the other component. This is the a squared plus b squared. Yes, it equals c squared, but to find c, I would take the square root. You might also look at this and say that looks an awful lot like the distance formula, and it does. It is the distance formula. Those two things are definitely the same. We just treat them a little bit differently when we talk about them. And so we're going to find a value for this. We're going to find it exactly. Somebody grab a calculator for us. What do we get when we get 11 squared plus 13 squared? 290. Does 290 simplify? It certainly divides by 10, but I don't think that's any helpful, is it? No, because I'm going to 29. So this is the best we can do. We're going to leave it exact unless we're told to round, and if we're told to round, we're going to pay attention to the number of decimals. Okay, is that all right? Okay, the next two are very interesting, E and F here. They ask us to illustrate something. Okay, now I've drawn an illustration of how we think about and where the magnitude situation comes from. That's good. But I'm also going to do this as a follow-up here on parts E and F as to how we talk about the addition or the subtraction of vectors and what that means visually. Okay, so we're going to do the addition one first. And we're going to actually draw in A and B vectors. So we'll start with A. So A is 2, 4. And I'm going to try to make it, pretty believable. So here's 2, 4. So the vector 2, 4 looks something like this. Okay, is that good? All right. Vector B is 3, -1. So when we're talking about adding vectors, what we do is we start at the terminal point of the first vector. So I'm going to start at this point. Where am I? Right here. I'm going to start at this point. And from this point, I'm going to move in the direction that B says. So what is the X direction that B says? What's my number? 3. So I'm going to go 3 in the X direction, like this. And then I'm going to go down 1. Does that make sense? Right? Addition means adding on to. So this is sort of a visual of adding on to.
So basically that terminal point becomes basically its origin point in a way.
Mm-hmm. So I think I've got one too many. 3. So I added 3 more over here. 1. No, what was I at to begin with? 2, 4. So I was at 2. So I need to add on 1 more. Yep. Okay. So I've added on 3 more. So here's 1, 2, 3. And then I need to go down 1 from there. So I'm going to end up right here like this. That's what it means visually to add on. We did A plus B numerically above. What was our answer for A plus B numerically on part A? 5, 3. Did we end at 5, 3? Yes, we did. We ended here at 5, 3. So visually, this is the resulting vector, or the resultant vector, right here, this pink one. Okay? We're at the end of time, so we will pick up with the subtraction one next time, and we will verify it because we didn't have a problem that actually told us to do the subtraction like we did the addition, and we can see that it gives us the same answer as well.